response to the video will be posted hopefully sometime later tonight. The reason I am so prolific is because I work with so many wonderful people. So in fact, I've got 4 students here who I'm sure it's completely randomly ended up next to each other. But I know you met some of them over dinner. We'll be around for a few minutes afterwards if you have any questions. But I don't have enough co-authors. So even though I have 17 students working with me on campus and another 20 plus working remotely, I need more. And so today there are some open problems which will be accessible to you. And I have worked on research papers with students in Hampshire College before. So if anybody is interested, you can connect with me by, I have to remember to point like this. My email address should be over here. If you can't remember that, what can you do? Yeah, I was going to say this is the 21st century. You should be able to find it. If you can't, then I don't want to work with you. Yeah, no, I'm going to be honest with you guys, okay? I feel like Cookie Monster, pairing over here is this. I will explain why Cookie Monster is on these slides later. Okay, so introduction. So hopefully everybody here has heard of the Fibonacci numbers. The Fibonacci Association, I'm going to be very careful because this is being recorded. The president does not have unlimited power. I do not have the ability to redefine the Fibonacci numbers. But there are a couple of acceptable definitions for the Fibonacci's. Everybody agrees each one is the sum of the previous 2. But there's a little disagreement as to how do you want to start. Some people go 0, 1, 1, 2, 3. Some people go 1, 1, 2, 3. Today, I want to go 1, 2, 3. And the reason is this beautiful theorem due to Zeckendorf. Every positive integer can be written uniquely as a sum of non-adjacent Fibonacci numbers. Okay. We need a number somewhat at random to decompose. Since I wanted to make the slides ahead of time, I had to choose a number. I chose 51. All right. Yeah, you got it. Okay, I could either choose 51 or 17. So I don't want to choose 34 because 34 is a little bit too easy to decompose into sums of Fibonacci numbers. Anybody have an idea of how we might try to write 51 as a sum of non-adjacent Fibonacci's? What should I do first? Yes.
Well, luckily we do have 34 here, so we could try to find what it is for 17 and then finish back on 34.
Okay, good. So another way of looking at this is a way to rephrase it, which I think is a better way of phrasing it. So subtract 34. Take the largest Fibonacci number you can, less than equal to your number, subtract that, and then we're left with, coincidentally, the number 17. And now, how could we decompose it? And if you notice, look at that wonderful LaTeX code. The 34 is now in red because we're using it. Ooh, right, yes. What should we do for 17? Yes. Well, no. You got to tell me one thing at a time. What should I do next? What's my next step? What should I do to decompose 17? Repeat. This is shampoo mathematics. Lather, rinse, repeat. Right? We threw away the largest number we could, 34. We look at what's left, 17. What's the largest Fibonacci number less than equal to 17? 13. And now you see the 13 becomes red. And now we have 4. And so now we do it with 4 and we keep going. We have 1 and we keep going. So at every moment in time, you do what is locally best. I throw away the largest. And I'll leave it to you as an exercise to prove that this always works, that no matter what number you start with, you will always end up with a decomposition. I'll leave it as an exercise to prove that the decomposition is unique. I will say briefly, one thing that you can notice very quickly is imagine we're trying to decompose. This is called the greedy algorithm. At every moment, you throw away the largest thing you could. If I threw away 2 adjacent Fibonacci numbers, then I must have done something wrong because at each moment in time, I'm throwing away the largest I could. If I could throw away 2 adjacent numbers, then I could have thrown away their sum. And that would contradict that I had thrown away the largest a moment ago. Okay, who here can convert miles to kilometers quickly? Excellent. Wait, exactly 1.6?
Like 1.608. I don't know. This was mentioned, I think, at the start of the program conversation. You can use the Fibonacci number.
Yes. And so if you shift every Fibonacci over by 1 in your decomposition of 51, because the golden mean, which is the ratio between adjacent large Fibonacci numbers, is approximately the conversion factor between miles and kilometers, you can convert 51 miles to 83 kilometers approximately by just shifting the summands in the decomposition. All right, I am trying to convince people, and I know I have at least one student here who likes to jog with me. A marathon is running 26.2 miles. A marathon would be running 26.2 kilometers. A marathon would be divide by the golden mean. And then a Camarafian is combining, switching to kilometers and dividing by the golden mean. It's about 10 miles. This is one of the worst applications of Fibonacci numbers possible. But it is an interesting historical quirk that the golden mean is so close to the conversion factor. How many of you have seen the Gaussian, the bell curve, the normal distribution? Okay. Anything that has this many names is probably important. A lot of distributions behave in the following way. So the actual functional form is given at the top. It's an exponential of x minus mu squared over 2 sigma squared, then the normalization factor. So this is a probability distribution. Mu is the mean, the average value. Sigma talks about how spread out it is. And a lot of things are normally distributed. If I were to look at grades, probably not normally distributed in a group like this. You'd be close to like a delta spike with almost everybody doing extremely well. But if I go to a large public school, you would have much, oh, this is being recorded. That would also be a delta spike because everybody does really well throughout every school in America. But if you look at heights, if you look at weights, you'll see distributions like this. If you look at batting averages, you'll see distributions like this. A lot of things are normally distributed. And it turns out that the summands in the number of Fibonacci numbers in the decomposition turns out to be normally distributed. And we will see a proof of that later today. We will see a really bad proof. So I was talking with some of you as we were walking over here, that frequently the first proof is not the good one. It's the brute force, throw the kitchen sink at it and just compute the hell out of it. And then after you do that, then you try to take a step back and see, is there a better way of looking at things? And so what I want to do today is I want to try to show you different perspectives. So first, yes, there's the brute force calculation, which we can do, but then is there a better way to avoid pages and pages of tedious algebra? Now, one way to avoid that is to have a lot of really good students working with you and give it to them as problems. And I've been doing that for well over 2 decades now. But at some point, the students revolt. And so you want to find other ways of looking at stuff like this. The next problem I want to talk about is gaps between summands. So if I look at my Zeckendorf decomposition, I could ask, how often do I have a gap of 2 between summands? How often do I have a gap of length 3, of length 4, of length 5? And it turns out that we're able to show that there's a geometric decay. There's 2 ways to do this. One is I can choose one number, and I can look at all of the gaps for that one number. Or I could take all numbers, and for each number, look at all the gaps and put that in a giant bin and see what fraction is there of the time do I have a gap of length 2? What fraction of the time do I have a gap of length 3? The more I average over, the easier it is. If I look at all numbers, it's much easier than looking at one particular one. For one particular one, it's possible that I might have different behavior, but most numbers should be close to the average behavior. And so my students were able to prove both cases, both almost all numbers are close to the average behavior, and if you just average over everything, which is much easier, then it's close to the average behavior. Who here has outstanding vision? Okay, for those of you with outstanding vision, can you look at the histogram on the left and see that it's decreasing by approximately 1.6 from peak to peak? So again, it unfortunately rained too much when I was walking here, and so I really am somewhat vision impaired right now. I've tried to clean this on a wet shirt, and so I can't see that well. How do you display information in a way that you can understand what's going on? Well, on the right-hand side, I plotted the ratio of gaps of length 2 probability divided by gaps of length 3 probability, gaps of length 3 probability divided by gaps of length 4 probability. And when you look at that, you see it's almost perfectly a straight line for a long period of time. Only as I start looking at really far down the line does it start to look different from the golden mean. And that's because now I have very few data points. I have very few gaps that are this large. And what's nice is we can investigate this on computers very easily. I'm not going to go too much into this. How many of you have taken calculus? How many? Oh, excellent. Not all of my students have raised their hand. Wow, I wish I had known that before I admitted you all. How many of you have ever had to take things like the derivative of the exponential of x? Have your teachers? Yeah. Here's a place where that actually arises. This is a natural problem where the exponential of an exponential arises. If you want to look at the longest gap between summands, it turns out it involves a double exponential. Okay, so there are several ways to phrase this. And again, I will post the video and I will post the slides, and all that. I view this as the cookie problem. They don't really like to use that phrase in math research journals. They call it the stars and bars problem typically. So the problem is if you have C identical cookies and P distinct people, how many ways can you divide the C cookies among the P people? And the answer is C plus P minus 1, choose P minus 1. And so I'm going to give you the combinatorial proof. And this is basically proof by story. So how many people have seen Cookie Monster? All right, for those of you who haven't seen, I am talking about the original classic Cookie Monster from Sesame Street, who is always up for eating cookies. All right, he would actually fit in very well in grad school. All right, so Cookie Monster, imagine you have C plus P minus 1 cookies in a line. Cookie Monster comes and he eats P minus 1 cookies. How many ways can you choose P minus 1 objects from C plus P minus 1? Well, this is the definition of a binomial coefficient. It's just C plus P minus 1, choose P minus 1. And so, for example, imagine we have 8 cookies and 5 people. So 8 plus 5 minus 1 is 12. Yes, excellent. All right. So Cookie Monster shows up. I actually went to, there is a National Bobblehead Museum. I visited it and I got permission. They wouldn't let me touch the Cookie Monster bobblehead, but they did pose Cookie Monster for me. Cookie Monster shows up. Cookie Monster eats 4 cookies. Everything up to the first eaten cookie goes to the first person. So the first person gets 2 cookies. Everything between the first and the second eaten cookie goes to the second person. It's not their lucky day, they get 0. And you can see that there's a one-to-one correspondence. Now, it almost sounded like somebody was a little bit upset that one person got 0. If that bothers you, you can actually impose a condition that everybody has to get at least 1 cookie. If you do, instead of dividing 8 cookies among 5 people, that's the same then as dividing 3 cookies among 5 people, because everybody starts off with 1 cookie. So you can incorporate constraints like that very easily, and that will be extremely important in a moment. So this is a great example of proof by story. Okay, so to put things into math speak, what we've really done is we've counted the number of solutions to a Diophantine equation in number theory. You know, I want my variables x1 through xp to be non-negative integers. I want them to sum to c. If you like stuff like this, you could then ask related questions. What if I want the sum of the squares to equal c, or the sum of the cubes? How would you solve problems like that? And you don't necessarily have the same techniques available. We can use this to give a much harder proof of the Zeckendorf decomposition. So why do I want to do a harder proof? I got to impress now. I want to do a harder proof because it's going to give me more information that I can then use to do other things. So I'm going to let P and K denote the number of integers between the nth and the n plus first Fibonacci number that have exactly K summands. And so this is a really important point here, is I want to localize. I want to look at numbers that are roughly the same size. If I want to know how many summands does a number have around 15 versus a number around 10 to the 15, I might expect a number of size 10 to the 15 is going to have a lot more Fibonacci numbers in its decomposition just because it's larger. So if I choose all of my numbers to live between Fn and Fn plus 1, they all have the same first sum. They all start off with Fn. And so I want to look at how many numbers in this interval have exactly K summands. And I'll do it, K goes from 0, 1, 2, 3, and so on. And so the largest summand has to be Fn. And then I'll let Fi1 through Ik minus 1 be the other summands. One of the rules of giving a talk is never, ever go through all the tedious algebra in public. Similarly, if you're in the audience, never try to follow all the tedious algebra if the speaker is violating the rule and giving it. I'm showing the algebra here, so if you want to look at it later, you can look at it later. You should be just trying to get at a high sense what's going on. I have my decomposition. And so I feel like, you know what, I'll go like this. I'm hoping I'm putting in roughly the right way. And so I have my indices. I know my last index has to be n. My first index could be as small as 1. And I know there has to be a gap of at least 2 between adjacent indices, because I can't take the same index twice, and I can't take something next to it. So I know ij minus 1 is at least 2. It turns out that this is essentially the same as a cookie problem. And I just have these constraints. This is equivalent to, I'm looking at all these gaps. They have to get me from 1 to n. And these jumps have to be at least of length 2, except for the first jump, which has to be at least of length 1. So at a high level, if I let d's be the distance between the amount I'm moving and the minimum amount I know I must move, then I can get this cookie problem that the sum of the d's is n minus 2k plus 1. So again, you just do the algebra And at the end of the day, when the dust settles, you then have that the number of integers that have exactly k summands is n minus k, choose k minus 1. This gives you a nice way to prove a nice binomial identity. How many numbers are there between fn and fn plus 1? So you can tell me how many numbers are there between fn and fn plus 1? Fn minus 1. So it turns out that if you sum all of these n minus k, choose k minus 1, that sums to fn minus 1. Every number is taken once and only once. And you can show that you can't have two different Zeckendorf decompositions for the same integer. So I've counted exactly the right number of decompositions. I've counted fn minus 1 decompositions. Every number has a unique decomposition. And I can now do a lot more. Because I know how many numbers have exactly k summands, I can try to prove their Gaussianity. So this is one of the most interesting talks I ever gave. This goes back to around 2009, 2010. I was at a conference in May, and my students didn't arrive until June. And I announced the result that they were going to prove before they even arrived on campus. I said, I know my students are going to be able to prove this. I don't know how much further they can prove, but I'm confident they're going to prove it. All right. So before I state the results, let me just make sure everybody's on the same page. How many people have not seen calculus? It's okay if you haven't. Okay, so there's a few people other than some of my smart-ass students. All right, so if you haven't seen calculus before, the little symbol after the squiggly sign, it's read the integral from 1 to n of f of x dx. This just means the area under the curve of the function f of x from 1 to n. And it turns out that we can use calculus to evaluate sums or to approximate sums. And so the first is the integral test. And again, if you haven't seen this, this becomes motivation for why you might want to take a class like calculus. If I add 1 plus 1/2 plus 1/3 plus 1/4 all the way up to 1 over n, it turns out that this is approximately the integral of 1 over x from 1 to n, and the area under the curve is just the natural log of n. And the way you prove this is you show that you can get upper and lower approximations. So how many of you have seen the integral test in your calculus class? Okay, so this is a nice application. We can use this to approximate. If you haven't seen it, this is motivation. We can approximate these sums by converting to integrals. So if I want to approximate n factorial, this is a wonderful lesson to get from today. Almost always in mathematics, if you see a product, take a logarithm. The log of a product is the sum of the logs. How many of you have ever tried to help like a 3rd or 4th grader with math? Okay, don't do that there. All right, do not explain multiplication to a 3rd grader by taking logarithms and then exponentiating. But in higher mathematics, we have a lot of experience with sums. Convert something to where you have familiarity. And so if I take the log of n factorial, then that's just the log of 1, log of 2, all the way up to log of n. Oh, I can approximate that with the area under the curve of log of x. Hopefully you won't be bored during the talk, but if you are, you can then try to figure out what's the antiderivative of the natural log of x, or more generally, what's the antiderivative of, say, the natural log of x to the kth power? Yes. Well, no, I'm just saying, I actually gave it to you over here. It's x log x minus x.
Log to the k of x.
Well, I'm saying this is the log of x to the first power. What if I gave you the log of x to the k power? There turns out to be tricks and formulas you can do for those as well. We can actually find the areas under the curve very well, and we can estimate n factorial by saying it's approximately, the log of n factorial is approximately the area under the curve, and we get n to the n e to the minus n 1 over e. If you do a little bit more advanced mathematics, you get it's about n factorial e to the minus n square root of 2 pi n. So it's actually very close. Just a little bit of other preliminaries, some notation. We say f of x is big O of g of x if for all x that are sufficiently large, the absolute value of f is less than or equal to some constant times g. So x is big O of x squared. If I give you x squared over 15 billion, when x is small, x is larger than x squared over 15 billion, but eventually the x squared over 15 billion will dominate it. The next one, as I mentioned before, the log of a product is the sum of the logs. And then the last thing which we'll need a little bit is we can Taylor expand, or we can approximate the log of 1 plus x. So if x is small, the log of 1 plus x is x plus an error of size x squared. Sometimes you need a little bit more accuracy, and you can write the log of 1 plus x is x minus x squared over 2 plus an error of size x cubed. And the whole point of this is these fall very quickly from calculus. One of the big themes of calculus is you replace complicated functions with straight lines or quadratics or cubics or polynomials, and you control how much the error is. How many of you have been doing probability now? We're almost done with the preliminaries. So if you have taken calculus and your teacher has not mentioned probability with area under the curve, you can sue. Okay, and I can help you with that. Okay, it's a crime. All right, this is one of the reasons why we care about areas under the curves. It gives us the probability of events. So we say something is a probability density if it's non-negative, if the area under the curve is 1, and then the probability we take on a value between A and B is just the area under the curve from A to B. And so here I've just given you a shaded region. So we want ways to calculate what is that area. The mean is the average value. The standard deviation is just how spread out things are. We don't need that too much today, but again, I'm just trying to put some extra information on the slides. And then independence is knowledge of one random variable gives you no information about knowledge of something else. All right. How many of you have seen Benet's formula? A good number of people. This is one of my favorite formulas in mathematics. So phi is the golden mean. It's 1 plus root 5 over 2. It turns out that there is a defensible metric where the golden mean is the most irrational of all irrational numbers. That you can defend that there is no number that is more irrational than the golden mean. Depending on your definition of where you start the Fibonacci numbers, we have a beautiful explicit formula for the nth Fibonacci number. And this allows you to jump to any Fibonacci number. If I asked you to calculate the first 10 Fibonacci numbers, is this difficult? So I sometimes ask my students, I will give you all A pluses for your entire college career if by the end of your 4 years at Williams, you can by hand calculate the first million Fibonacci numbers. Do you take me up on that offer? So you want to estimate how many because these are, oh no. How many calculations would it take? And we will assume that you make no mistakes, in all your arithmetic, because of course, one mistake and you're dead. But in principle, theoretical mathematics, it's trivial to calculate Fibonacci numbers. Just plow through them. But to actually do the calculation is painful. It's time consuming. Benet's formula allows you to jump to any Fibonacci number. The proof is brilliant. So here is Benet's formula. One method of proof is the method of divine inspiration. So the way divine inspiration is you go like this with your chin, or sometimes with your cheek, you go, and then you write down the answer. And so all you have to do now is check and see when n equals 0, this gives f0. When n equals 1, it gives you f1. And then check and see that these numbers satisfy the recurrence relation, and they must be the same. What's the problem with the method of divine inspiration? Yes, it's hard to be divinely inspired. And so, how do you know you'll be divinely inspired on the next related problem? We want a procedure that will give us divine inspiration. Fasting, going up to mountains. We've got some mountains in the area. Are we allowed to have the students fast? Actually, the dining hall proof is actually pretty good, so I don't think you want to fast. Here is a beautiful way of proving Benet's formula. So we create what's called a generating function. So have some of you been doing generating functions? Excellent. So at first, this looks like this should not work. I don't know the Fibonacci numbers. So how do I put a function where the coefficients are the things I'm trying to understand? Well, it turns out we do know the Fibonacci numbers. We just don't know that we know them. As soon as we write down the initial conditions and the relation, the recurrence relation, we know everything about them. We don't need to extract it. So the hope is that I can use this to get a closed form expression for g of x. And then once I know g of x, I can somehow use that to get information about the individual coefficients. And so I put in my series expansion. And again, this is where you don't watch the algebra too closely. This is just for completeness. The algebra is here. Notice some of them are they're all starting at 2. G of x starts at 1, so I've got to play some games. I've got things shifted a little bit because of the recurrence relation. I have an fn and I have an x to the n plus 1. What should I do to that xn plus 1? Its coefficient is fn, but it's x to the n plus 1. What should I do to it? I'm sorry? not the logarithm. So the left-hand side is nice. The index of fn is the same as the power of x. But the next term, the index is n, but the power is n plus 1. What could I do?
Take out an x.
Take out an x. And what should I do for the second one?
Take out 2x.
Take out 2 x's. And so when I do that, I then have an x and an x squared. Notice that those are almost g of x. They're g of x up to a couple of terms in the beginning. So I just add the terms that I'm missing. And I've got g of x on both sides. I can solve for g of x, and I get g of x is x over 1 minus x squared. All right. Who are my calculus students? Who has done calculus? What is your least favorite integration technique? Not by part, no, parts. Partial fractions, right. This is a nice application of partial fractions. So if I take my closed form for g of x and I use partial fractions, I can now write it, and now I can use the geometric series to expand both of them. If I try to geometrically expand is a legitimate phrase, the x over 1 minus x squared, that's going to be bad because the x and x squared have different degrees, and when I expand it, things are going to interface terribly. But now I've got very simple, when I expand it outward, I get a beautiful closed form expression. And this is one way to get Binet's formula. All right, we now have all the preliminaries to do the Gaussian behavior. Yes?
Wait, sorry. Like, how does the partial fraction expansion lead to this direct?
So I've got the x over 1 minus x squared. I use partial fractions to expand, to write that as the sum or the difference of two fractions.
Yeah.
And each one of those, rather than having a quadratic denominator, which I had initially, I now have two linear denominators. And I can expand each one of those using the geometric series, and I'll get an x term, an x squared, and x cubed. If I take the original one and I take my r to be x plus x squared, oh God, when I expand, I get x plus x squared, then I'm going to get x squared and x cubed, and x to the fourth is the next term. And there's going to be a lot of talking between terms.
So we can get like the coefficients of the generating function.
Yes. And when we expand it out, and that's where we get this. What kind of numbers are the Fibonacci numbers? Integers. Does this look like an integer? I've got square roots, I've got divisions. Everything works out at the end of the day. All right. So now I can give you the proof that my students gave, that I knew they would give before they even arrived on campus on Gaussian behavior. And so I was at the 2010 Combinatorial and Additive Number Theory Conference, and I said, please, nobody in the audience work on this. My students will be proving this in about a month. And they will prove that as n goes to infinity, the number of summands in the Zeckendorf decompositions converges to a Gaussian. And here's the proof. Use Stirling's formula that n factorial is about the following. We know that the number of integers in the interval that have exactly k summands is n minus k, choose k minus 1, and then just simplify. And so this is where it's nice to have students. So I'm not sure how visible this is to you, but they started looking at all the algebra. And so they looked at, turned out it was sometimes easy to shift indices a little bit, doesn't really matter. And they have this expression, they put everything in, and they start using Stirling's formula to approximate all the factorials and all the powers and everything. And then they start doing the algebra, and they start working on the different pieces. And then they do some more algebra, and they start taking logarithms, because when you have products, you always take logarithms. And then when you have logarithms and you want to expand, you look at where the mean is and where the standard deviation is, and you try to normalize things, and you keep playing games. And then you rewrite things so that you have the log of 1 plus something, or the log of 1 minus something, so that you can hopefully expand. And then you start expanding, and you're keeping track of what the main terms are. At this point, the students then come to your office upset, and you send them away. And then they come back a little bit later. And at this point, everything has now finally been done. You can look at this slowly if you want to. The goal of today is to have you come up with a way to bypass this. So it might be possible. What I want to do now for the remainder of the time that I have is I want to talk about gaps in the bulk. And I said that this is a geometric decay. And I'm going to show you the long way to do this and a new faster way. And I think you might be able to apply that faster way to bypass a lot of these calculations of pages. I'm actually writing a book right now, because that's basically what I do. And this book is on Zeckendorf decompositions. And that's what actually inspired this talk, is I had to go through these papers and put it in book form. It's like, oh God, this is painful to write up. Is there a better way to do this? And it's like, yes, there is. There's a nice backdoor approach. And I hope that you guys can push it further. So imagine I give you F1 plus F8 plus F18. So there's 3 gaps. The gap from F1 to F8 is a gap of 7, and from F8 to F18 is 10. So I'm looking at the gaps between indices. And so what I want to know is, how often do I have a gap of length k? If k is 0, how often will I have a gap of length 0 in a Zeckendorf decomposition? 0 times. A gap of length 1, 0 times. All right, so I'll do the rest since you guys did 2 of them. All right, so the hope is that there's going to be some limit as n goes to infinity of what's the probability we have a gap of length k. And you can ask this for other problems. I'm going to skip all the other problems in the interest of time. And there's a beautiful result, which as a Bostonian, it's hard to say his name, Lekkerkerker. The total number of gaps between Fn and Fn plus 1 is Fn minus 1. Well, okay, Fn minus 1 is the number of numbers we have in the interval. And then it's n over phi squared plus 1. So this is basically telling us, on average, each number has approximately n over phi squared plus 1 summands. If you have n indices, what's the maximum number of indices you could have in a Zeckendorf decomposition? The largest you could have. N over 2. What's the fewest? 1. Halfway between n and 1 is n halves. This is about 0.276n. So it's a reasonable number. And again, you always want to try to do sanity checks. So the total number of gaps is Fn minus 1 times n over phi squared plus 1. And so whenever you do combinatorics, you always want to be careful to make sure you don't double count. And so I'm going to let xij be the number of integers in my interval, where m's decomposition includes fi and fj, but nothing in between. So that will be all of the integers that have a gap of length, j minus I, starting at fi. And so if I want to find how many gaps of length k there are, it would be xi, I plus k. So I want to start at I, end at I plus k, have nothing in between. I want a probability, so I divide by the total number of gaps. And then I look at all possible starting values. I don't have to go beyond n minus k, because if my starting index is beyond n minus k, if I move k forward, I go beyond n. So I need to calculate how many integers have a gap of length k starting at I. Right, this is an example of a picture's worth 1,000 words. If you go forward a few slides, you can see text. Nobody wants to see text. Let's talk about it. So I'm looking at the indices from 1 to n, and I'm going to color in all of the indices I know I must choose. I have to choose fi. I have to choose fi plus k. I have to choose fn. I'm going to cross out all of the indices that I can't choose. And anything that's left over, these are the unfilled circles, I can either take or not take, subject to the rule that I can't take 2 adjacent. So much of math comes down to, can you look at things the right way? I am sure that there must be cube enthusiasts here, correct? People who do Rubik's Cubes. This is probably one of my favorite Rubik's Cubes. It's 2 by 3 on sides. And I know this is not being shown on the video. I don't really want. How many people have seen this cube before? When you try to turn the red side, it doesn't work. But if you hold it at a 30 degree, you realize, oh, it really is 3 by 3. But you have to look at it the right way. This is essentially the same as a standard 3 by 3 by 3 cube, if you hold it at 30 degrees. If you don't notice that, it looks very different, and you can start turning it into a ninja spike, and you can get interesting conversations with airport security, which I will talk about when this is not being recorded. Over here, does anybody know how many ways there are to fill in the circles legally up to fi? So I have to choose fi, and I want to fill in the circles legally, so I never choose 2 adjacent. You actually know the answer. The answer has been said. I'm sorry? Not the C+1. It's not a combinatorics. Thought? How many numbers are there between fn and fn plus 1? Fn minus 1. And all those numbers have Zeckendorf decompositions where their largest summand is fn. I'm choosing Fi, everything else is free. This is equivalent to putting in all legal Zeckendorf decompositions between numbers between Fi and Fi plus 1. So the number of ways to legally fill in the stuff in the far left is just how many numbers are there between Fi and Fi plus 1. It's just Fi minus 1. Okay? Does everybody see roughly that it's really the same problem we did before? For the stuff on the end, I can't have Fi plus k plus 1. I can't have Fn. It's really another problem like that, except I have to play the shift the index game. And again, nobody wants to see algebra in public, so I will just say that when you play the shift the index game, you get Fn minus k minus 2 minus I. And so I can choose the left in Fi minus 1 ways, I can choose the right in that ways. So the number of ways I can legally fill in the rest is their product. And that will give me how many numbers have a gap of length k starting at I. It's the product of two Fibonacci's. So now all I have to do is I plug that in. So I have a sum of product of Fibonacci's. I divide by Fibonacci times n over phi squared plus 1, and I take the limit. And when you do that, you get 1 over phi to the k. It comes out beautifully. Now, unfortunately, we need a lot. We need to understand the sum of a product of Fibonacci's. Well, we can use Binet's formula that writes the Fibonacci numbers as the sum of two exponentials. We multiply them so we get 4 exponentials. So I sum 4 exponentials, not a big deal. And then lots of other stuff to do, take the limits, have all the dust settle. All right, so rather than doing all of that, I want to show you a backdoor. So how many of you have seen basic probability? You have a density, the area under the curve equals 1. How many of you have seen this? Okay, so for those of you who haven't seen this, if you want more information, please let me know. My first year at Williams, I was teaching a class on differential equations. This was before everybody had phones. We had what was called clickers, and you could ask questions. And linear algebra was not a prerequisite for differential equations. I wanted to talk about systems of equations. And so I wanted to make sure people were comfortable with 2 by 2 equations. And I said, how many people want a review of 2 by 2 equations? No one. So everybody's fine with 2 by 2 equations. Nobody wants a review. Okay. Using your clicker, I'm not going to report the results to the class. I'm just curious. Press 1 if you want a review, 2 if you don't. I never said I wouldn't tell other people. I just said I wouldn't tell the class. 43% wanted a review. 0% were willing to admit that they wanted a review. I was much more intimidating back then. If there is something that you want a further explanation of, you might have people rolling their eyes next to you, probably not because this is a family program, but almost surely people around you will be very happy that you asked, even though they would never ask. So please, if there's something that you're trying to understand, please feel free to ask. So a probability distribution, the area under the curve, or if it's in sum, it has to be 1. So a lot of times, it's called the theory of normalization constant. If I have something that's non-negative and the area under the curve is equal to 2, if I multiply by 1/2, it's a probability distribution. If the area under the curve is 1/2, I multiply by 2 and it's a probability distribution. Okay, I might have said it wrong the first time. And so a lot of times, if you can guess the functional form, if you can find the x dependence, you can then figure out what the normalization constant is. And so I'm not going to go into too much detail on this because not everybody has done calculus, but I want to give you a quick sense. This is called the chi-squared distribution. Has anybody here seen the chi-squared distribution? All right, so for those of you who've seen it, this is absolutely wonderful. It turns out that the sum of chi-squared distributions is a chi-squared distribution with a different parameter. It turns out when you sum two probability distributions, the new density is this integral. It's called the convolution. I'm not going to go through all the details. You plug everything in and you need to do this integral. And when you look at this integral, you've got the integral from 0 to x of t to the negative 1/2 x minus t to the negative 1/2. This does not look like a pleasant integral to do. But if you make the substitution t equals x times u, then t going from 0 to x is the same as u goes from 0 to 1. Yes. Did I make a mistake?
Like the beta function at 1/2.
It is the beta function at 1/2. Yes. Or actually, not the beta. Well, the beta function should have two parameters.
Well, beta
Yes.
1/2.
Yeah. 1/2. Yes. Yes. And so if I do this change of variables, now all of a sudden I can pull out all the x dependence and I have this integral involving u. And this is where I got to be careful what language I use because this, I don't care. It's some number. I'm going to call that fancy C sub 1, fancy capital C sub 1. It's just some number. The key thing is I've pulled out the x dependence. Who can recognize what kind of distribution this is? For those of you who are doing probability. What kind of distribution is that? You have an e to the negative x halves. This is a not normal. Normal is e to the you can say, what do you think it might be? So we have e to the negative x halves. Who here is doing probability? Have you seen this one? No? So this is an exponential distribution. So it's either got parameter 2 or parameter 1/2, depending on how you pronounce your exponential distribution. It's a well-known distribution. I don't care what the u integral is. I know that this has to integrate to 1, so I can figure out what C1 is because I know that this has to integrate to 1. And so I don't have to do this difficult calculation. I can bypass this. At the end of the day, it's an intermediate step. I don't care about the value of the intermediate step. I care about the final answer. And so a lot of times, the way we solve math problems is we calculate a lot of things we don't need along the way. And the whole point of today is we can bypass a lot of that. And here's the beautiful trick. What I'm going to do is I'm going to calculate the ratio of a gap of length g divided by a gap of length g plus 1. And I'm going to show that that ratio is phi. So remember long time ago when we just met, I showed you 2 different plots of the gap. There was the histogram, and I said, does anybody have good enough eyesight to see that it's decreasing by the golden mean? And then I had the other one where I plotted the ratios. They're both equivalent. If I can show that the ratio is always the golden mean, then I know it's a geometric decay with geometric decay parameter of the golden mean. And so look at the calculation I need to do. I've got the sum of a product of Fibonacci's divided by a sum of a product of Fibonacci's. Well, those sums are pretty similar. They both have an fi minus 1. The real difference is if I want a gap of length g plus 1, I just make my middle 1 unit longer. And so I hope that's because of how good of a talk I'm giving, not how much time is left.
Last figure did it.
So the whole point is that if I want to find a gap of length g plus 1, I'm just making the middle 1 unit longer. So when I look at what's going on the right-hand side, it's just 1 unit smaller. So its index decreases by 1. And that's why I have a g plus 1 rather than a g. Okay, well, each Fibonacci number is approximately the golden mean times the previous. So now, the g plus 1, its index is going to be a little bit, it's going to be 1 unit smaller. So each summand is going to be approximately the golden mean smaller than the corresponding one upstairs. And that's where you're going to get this ratio of the golden mean to come from. Now, you do have to be a little bit careful. Which has more terms, the bottom sum or the top sum? So which has more terms, the bottom sum or the top sum? The top sum. The top sum has 1 more term, but the contribution from that 1 extra term is really small. If you have n terms and n is huge, 1 little term is not going to make a huge difference. And so you can ignore the fact it's not going to really affect any of the limits. What really goes on is because the bottom has an index that's 1 smaller, each summand is approximately the golden mean smaller than the ones upstairs, or the golden mean upstairs, the ones upstairs is approximately a factor of the golden mean larger than the ones down below. And thus this ratio should be the golden mean. And it all works out. And this is a way to bypass all of those calculations. I no longer need to figure out what is the sum of products of Fibonacci numbers. I can bypass all those calculations. So future work, so I still got some time left. Can you do this for other recurrence relations? So it turns out that we did this for the Fibonacci numbers. Similar results hold for other recurrence relations. Can you generalize this argument? I believe that shouldn't be too bad. Can you apply something like this to the longest gap problem? Can you apply this to the Gaussianity? The Gaussianity calculation, if you enjoyed that, you need help, and there are people around who can help you. Okay? In some sense, it's not bad. It can almost be kind of cathartic to do those calculations until you make a mistake and spend an hour and realize that you don't know where you made the mistake and you have to try to track it down, and then you make another mistake, and it just takes days before all the algebra works. In principle, it's straightforward. I can see my students nodding who've been working on some of these very technical calculations, but in practice, you will make mistakes. This is one of the reasons why you want to learn how to code and program some stuff so that you can just check your calculations as you're going, put in values, see if things are right. Can you take this idea of normalization constants and somehow come up with the fact that I can bypass this and show that the ratios are appropriate and get Gaussian behavior? I was able to show the ratio of a gap of length G+1 and G gave me the golden mean and gave me this nice geometric decay. Can we do something similar and get this Gaussian behavior for just the number of summands? I would love to see that done. And so if you're interested, I would love to work with you on a research project like that, either during the semester, when you get back to school and have all this copious free time, because of course we have so much free time during the academic year. If you're interested, I've just posted a bunch of references, and then if you have any questions, my students and I are happy to chat. So thank you.